Okay, you're good to go, Jim.
Alrighty, so actually before I dive into this, I wanted to follow up a little bit on the last few questions from for Fred about compute time, and I think so. I think I'll talk about this more on Thursday, but I think generally we're starting to get a handle on what our compute budget really looks like by comparing it to actual processing of our pipelines today on precursor data, and even comparing to some external ones. What we have not done yet is, and I think is almost impossible to do at this stage, is try to assign budgets to different parts of the pipelines. Too many of them are just too uncertain. So I think just running Scarlet as it is right now is probably feasible within our compute budget, but that would crowd out a lot of other more expensive things we'd like to do as well. And we just don't really have a good sense for how things shake out. And of course, if you did want to do things in multi-scale and model the individual things, model individual objects at W1st scale, and then project them to also deblend on LSST images, that's going to be much more expensive as well. All right, so that said, I'm actually here to talk about building and using coadds, which is a step I think that is familiar to most of you and is a key part in actually not blowing our compute budget, because anything you do on a coadd should be a lot cheaper than doing it on individual images, and there's a huge amount of work that we can do on coadds. So what will we use coadds for? So first off, most of our objects, remember objects are the name we use as opposed to sources. Objects mean essentially catalog records that are characterized using all the data we have available rather than a single epoch. Most of our objects are detected on coadds. Some of them will come from matched difference image detections. None of them will come from single visit direct detections. I think we expect everything that we could get from single visit direct detections will be better detected either in coadds or on difference images. We're going to use coadds when we make difference images because we need a template, and we're going to use the coadds as the templates. Objects are going to be almost entirely deblended on coadds. There's a little bit of an exception for crowded fields. Colin will talk about that on Thursday. And objects are mostly measured on coadds. And I think some object measurements are derived from force photometry on single visits, but most object measurements will also come from coadds. All right, so in terms of the rest of this talk, it's sort of three sections. The first one is I want to talk about different flavors of coadds and what we do right now. Then I want to talk, this is sort of introductory, a little bit more pedagogical, and then I want to talk about what's working well in our pipelines and what isn't working well. A lot of these are just the problems that come up when you get to a certain level of sophistication. You come into encounter problems at the next level of sophistication. And then finally, I want to talk about our future plans, and including one prominent anti-plan, something that we've talked about doing in the past but no longer plan to do. So, flavors of coadds. So I want to start with what I call direct coaddition. You're all familiar with it. You might not be familiar with this name, but I think it's good to have a name for this kind of coadd because we all talk about it a lot. This is where you just resample the images and then combine them. But I want to point out that I think it's really critical that you combine them with a linear statistic, a weighted mean, with no outlier rejection at all. That's necessary because it's the only way you propagate your PSF. I'll talk about that in a moment. It's also, I think, the only thing that makes sense. If you have images with different PSFs, the ensemble of per epoch pixel values that contribute to a certain point in the coadd aren't drawn from the same distribution. Or they're drawn from, some of them are drawn from different parts of the PSFs that are in different parts, that are different in different images. So no kind of outlier rejection, no medium stacking, none of that actually makes sense on these kinds of coadds. For similar reasons, it's really important to combine these with per image weights or maybe very large spatial scale weights, not per pixel weights. If you add with per pixel weights, again, you're combining images that are drawn from different pixels that are drawn from different distributions, and it doesn't make sense statistically what you've done. If you follow those criteria, you can propagate the PSF model at a point on the coadd by evaluating the single visit PSF models and then resampling and combining those images with the same weights. Convolution is a linear operation, and so if you make sure that your coaddition is a linear operation, you can propagate your PSF this way. As a little bit of an aside, there are different ways people define PSFs, and it's actually critical here to define your PSF to include the pixel response. People like to think of pixels as rectangles because when you zoom in all the way in DS9, they look like little rectangles, but pixels are not rectangles even on single images, and they definitely aren't rectangles on coadds. The big problem with this that I'll get back to quite a bit later is that the coadd PSF is discontinuous where the set of input images changes. Either you've got, the edge of a CCD, or you've got a bleed trail or a bad amp or something like that. Whenever that happens, the number of inputs change and the PSF changes from, a set of n images to a set of n minus 1 images, and that's a discontinuous change. In terms of signal noise, direct coaddition is not optimal, but it's not bad. How bad it is actually depends on the seeing distribution. The easy way to think about it is if you weigh these images by exposure time when you come in your weighted mean, there's usually better choices to weigh by exposure time. I don't think anyone actually does that. But if you did do that, it would be just like a single long exposure. And as a practical example, the HFC wide survey loses about 1.5% in signal noise relative to the optimal of if they combined all the images ideally. Next up, PSF-matched coaddition. In this case, after warping, you match all the input images to a target model PSF. That's usually some analytic PSF. By matching, I just mean you convolve with a difference kernel. It's necessary for the target PSF to be at least a little bit larger than any input kernel, or at least very close to that. And that means you have to throw away the worst seeing images. You don't have to propagate the PSF model in this case. It's just the target PSF. And there's no discontinuities in the coadd PSF. This is a real big advantage of this approach. And you can use the same target PSF across different bands if you want to get consistent colors. This is something I'll talk about on Thursday. I have a suspicion that Conrad will talk about it as well, although perhaps from a different angle. Another thing to point out here is that outlier rejection is mostly reasonable for building these. I only say mostly because here the different input pixels that contribute to one output pixel still aren't drawn from the same distribution. In fact, they'll be correlated with the other pixels on the same epoch as them, but they are drawn from different distributions with the same mean. And so what sigma you might want to clip at and what your median actually means is not necessarily what you'd predict, but it's not a crazy thing to do outlier rejection because at least they should be drawn from this distributions with the same mean. In terms of signal noise, matching is theoretically fine for signal noise. Convolving them with a known matching kernel is a reversible operation. But by doing that, you move noise from the variance to the covariance, and that means you have to track that. And nobody actually does that in practice. If we did track the move from the noise, to the covariance, and made use of that in all the downstream processing, you would not lose any signal noise from PSF-matched coadds. And I think that's a common misconception that by blurring the PSF, you made things worse. That's not true. You've made things worse because you didn't track the noise correlations. Now that's mostly an academic point because it's pretty much impractical to track the full noise correlations. Maybe it's interesting to consider whether you could track some of them and whether that'd be good enough. But I think for the most part, you use PSF-matched coadds in places where you don't care about high signal noise because they have other advantages. And even if you did track all the correlated noise, you'd still lose a little bit of signal noise because you have to throw away the worst images. Wouldn't contribute very much to begin with, but you do have to throw them away. All right. Now we're getting into something that both of those I should mention, these little green check marks at the top. Those are there because we have implemented these in our pipelines and we use them in various places, and I'll get back to that later. Now we're moving into flavors of coadds that we don't yet build, but I think understand well enough that we could build if we decided it was worth the effort. So if you want to do optimal detection for isolated point sources, the way to do that is, in the limit where you have background dominated noise, what you can do is you correlate the image with its own PSF, and that yields what we call a detection map. The pixel values of those images are proportional to the log likelihood of there being an isolated point source centered at that pixel. If you want to do that for multiple epochs, the right way to do that is to create those detection maps for every single epoch and then add them, because by adding those log likelihoods, you're multiplying likelihoods, and that's the right thing to do with likelihoods. It actually turns out that if you want to do something other than just detect isolated point sources, maybe detect non-isolated things because they're blended or extended sources, you can actually do everything you might want to do on that coadd as well if you've propagated its PSF through too. And in fact, this is a piece of a larger result that any operation that assumes background dominated noise and a static sky can be done on that coadd with no loss of information. This detection map coadd is a sufficient statistic for the true sky. But there are an inconvenient sufficient statistic. By convolving with the PSFs, or sorry, correlating with the PSFs, you end up with an image that has such highly correlated noise, you can't really use them the way we normally would. You can't do aperture photometry or measure moment shapes and understand what you've done in the usual way. But to solve that problem, you can decorrelate after coaddition. And this is a result that was due to Nick Kaiser a number of years ago. It's been rediscovered a couple of times. The idea being that if the input noise in the PSFs are spatially constant and there's no missing data and no edges, this is all straightforward in Fourier space. I can tell you later, but I didn't want to go through the math right now, that you can decorrelate the image to get white noise and an optimal combination of images and a sufficient statistic for all of your input images, again, under those assumptions. Now, the assumptions I've limited are all locally fine. You know, in most of the area of the survey, you're not going to have significant variations pixel to pixel in noise and not significant variations in PSF, and you'll be far from an edge, but you actually have to make this work over the whole survey, and that's what makes this algorithm complicated. I think it is feasible, but there's a lot of bookkeeping involved, a lot of careful padding and other sort of, you know, subtleties of doing Fourier transforms in the real world on real data. Those were all discussions about single band coadds. And if you want to detect across multiple bands, it does make sense actually to combine coadds of multiple bands. And actually the right way to combine them is pretty straightforward. It's just a matched filter. You want to combine them with weights that correspond to the SED of the thing you're trying to detect. Now that isn't great for if you're trying to make a general purpose survey pipeline, because you want to be able to detect lots of different SEDs. And so there's a few options there. A chi-squared coad is a particular weighted sum that's optimal for the SED of the sky. That doesn't sound like it's something that makes sense. It makes sense if you frame detection as rejecting the null hypothesis that a pixel is sky. It's not the way I normally think about it, but I think you can put them on in equivalent terms by saying it's optimal for the SED of the sky. You can also imagine making multiband coads for specific idealized SEDs, maybe just something that's red with some linear slope. All of these ideas of combining coads across bands are easy to implement. I think the hard part is just guessing what's best for science and which combinations are worth actually doing. All right, so I've talked about a lot of different kinds of coads, and I want to run through real quickly what we have implemented and where we're using things. So today, we use direct coads for almost everything. We use them to detect on. We don't make those optimal detection maps yet. We actually just make a direct coad and then smooth by the PSF. We use them for deblending. We use them for measurement. We use them actually as the templates for difference imaging. The one place we don't use them, and I'll talk about this in just a moment, is as a subtraction template for artifact rejection. There we use PSF-matched coads so we can do outlier rejection. In the future, it's possible we could continue doing the same thing, but I think we're evaluating our options for using those fancier likelihood optimal detection coads for detection, the decorrelated Kaiser versions of those for deblending and measurement. And I think there's a number of different options for difference imaging. You could imagine going to PSF-matched coads so you can get rid of artifacts better, and so you can avoid discontinuities in the PSF. You can imagine going to decorrelated coads so you can get higher signal noise in your template, and it also gives you ways to avoid discontinuities. There's also an idea for more model-based PSFs, model-based coads that Ian Sullivan will talk about on Thursday that will include DCR correction when we make the coads. I think for artifact rejection, we're probably going to just continue to use PSF-matched coads as that's working pretty well. So specifically, what's working well and what isn't? Rejecting those artifacts. So this is a procedure called compare warp. It was developed primarily by Yusra, who you've already heard from today. And the idea is that we start with PSF-matched warps and a sigma clipped PSF-matched coads. This is very aggressive sigma clipping. While we don't have to worry too much about what it might do to even our analytic PSF, it shouldn't do anything, but the point is that this is essentially a throwaway thing. It's an intermediate that we difference against each of these PSF-matched warps. And that gives us what we call warp diffs. And so you can see that this highlights all the temporal stuff both the garbage like this interesting swallowtail ghost and a lot of real temporal detections that are too small to see in these images. From there, we can detect sources on those, both positive and negative sources, and that generates artifact candidates. And then you can see, this is a count map of in how many of these warps, these PSF-matched warps, of these warp diffs, was a pixel detected as a temporal artifact or a temporal object. We can filter them based on the number of epochs in which each of those appeared. We can create a mask from that, and then we can combine them. So you can see here's a coad produced from that, and here's an image that shows the number of images that went in. You can see how that includes lots of artifacts that are not at all apparent in the actual image. And here's a blown up version of that. You can see that there are some nice ghosts, which are not at all apparent in the coad. We've gotten rid of them by finding them and masking them through this procedure. We're pretty happy with how this works, but it's not perfect. And it's limited primarily by big bright objects and dithering. So a really bright object that overlaps a transient or a temporal artifact that we want to get rid of can result in the artifact we want to get rid of being labeled as persistent, because of course the big bright star is going to appear in every single image. It's going to look a little bit different in every image, and it's not going to subtract cleanly. And that, people who do difference imaging are quite familiar with big bright stars not subtracting cleanly. Also, if you don't have very big dithers, your ghosts all land in the same place. And that's what happened in this data. This is the HSC ultra deep fields where the dithers were quite small, and the dithers all landed in the same place more or less, or maybe it looks like a slightly different place depending on the band. And the result was that we weren't able to match them and they printed through. So those limitations were based on really trying to do this almost entirely with temporal information. The next obvious step is to use morphology. We do this a little bit already with cosmic ray detection. We actually do morphological cosmic ray detection much earlier in the images, much earlier than image processing. But it's going to really be necessary to do more than that, because anything that we found here to get rid of and keep out of the coads is going to come back when we do difference imaging for science, because these are all temporal artifacts that are indistinguishable temporally from real transients and variables that we want to find. One big piece of that is ghost prediction. There's some work for HSC in progress at an AOJ. I imagine the LSST work on ghost prediction will ramp up once we have an actual camera and data from it. There's probably some steps we could do before then, but I think it's really much more valuable to spend time on this when you've got real data. Satellite trail detection is another interesting piece of this. This is actually mostly working, it's nearly integrated. It wasn't in the versions of the pipeline that produced the slides I just showed, but we do have it running on a branch. Here's a coad that was built with the current stack, and here's the one with the branch where we've very clearly gotten rid of that satellite trail. This is work from Claire Saunders, who has been just joined the DM team recently and has gotten this, again, a code she had working before she joined us, up and working with our pipelines remarkably fast. All right, so that was a success story. Now I'm going to talk about some things that are, well, it's probably not quite right to say that they're not success stories. I think they're problems that we've encountered because things are working well enough for them to become our biggest problems. But they are certainly problems we'll have to solve. So first off, noise is correlated. This is true even in direct coads, because if you resample images with a non-perfect kernel, essentially anything other than a sync kernel, you're going to get some correlated noise. This is fairly significant. It results in some uncertainty estimates for all of our coad measurements because they're all using an incomplete view of the uncertainty. This all comes from the fact that we've moved noise from variance to covariance, and our data structures don't hold the covariance. I think it should be possible to approximately propagate it. This is not, it's not hugely correlated. I suspect one or two off-diagonal elements is enough. I think it's also intriguing that whether we could use Kaiser or decorrelated coaddition to get rid of this entirely. That's sort of like using a sync kernel or something more like a sync kernel when you actually make the images, and going, I think, into further detail on that as our scope. But I think it's at least an intriguing possibility. I'll talk more about the actual effects of this in my galaxy photometry talk, but if you, for the most part, if you look at results coming out of our pipelines and you see our uncertainties are underestimated, this is almost certainly the big part of why. PSFs and resampling. Our PSF metrics don't look as good as on coadds as they do on individual images. This is mostly a talk about weak lensing PSF metrics, so I'll talk about this more in my shear estimation talk on Thursday. I think we have some candidates for what's going on here, but this is where we're at right now with the coaddition of PSFs. Finally, CCD boundaries and masking produce PSF discontinuities, and we know where those are, and we set a mask bit on any object that's on or near a discontinuity. And for a lot of science, they don't actually care about those discontinuities because these are small changes in the PSF. And you can imagine that when you've got, n images going in, the biggest effect you could have is sort of a 1 over n effect. And for LSST, that might be small enough that it won't be a problem even for weak lensing. But I certainly wouldn't want to bet on that. And I don't think anyone's done any studies to get at that. And so for weak lensing at least, and probably a few other very demanding systematic science cases, we will have to figure out what to do with these objects that lie in discontinuities. And that's because this approach to just setting a bit works for HSC because we've got about 5 or 6 epochs deep in most of the sky. And that results in the masks that look something like this. This is a coad patch. It's something like 10 arc minutes on a side. When you have 10, you get a few more. You can see here there's also bad amps getting moved around here. Our coad PSF propagation does not account for masks. And right now we use this masking to deal with, it doesn't account for masks in propagating the PSF, which means we have to set a different mask bit to say we didn't account for this bit that we should have. And that's how we deal with the bad amps. So the bad amps grow too. That's maybe not intrinsic, but it's the way things work right now. And of course, you can see as you go up to 50 or so epochs, you just blow away your entire sky. Every object lands on an edge. So if you have to throw away objects that landed on an edge, you have nothing left. So there's another little problem with this, and that's the computational performance. Every time we evaluate the PSF at a point on the coad, we have to go back to evaluate the PSF model on the single epoch images, transform them all the way through this, and average them the same way we did the coad. And so we're essentially re-coadding the PSF models every time we evaluate them. And this is actually quite slow. People who have been doing the DC2 processing and people who have been doing the HSC official ultra deep processing have really been hit hard by this. It's when there's a large number of epochs, this is the single slowest part of our pipeline. Alrighty, so I've talked about lots of problems, and now I'm going to talk about the ideas we have for fixing them. First off, discontinuities. An obvious thing to do is to make per object coads. And the idea here is that you use a regular coad, a likelihood coad, a direct coad, whatever for detection. Then you use that same coad or a similar one for preliminary deblending and measurement. And now you know where all the objects are and roughly how big they are. And you can make postage stamp coads for every object. And when you make a postage stamp coad, if any input image lies on a discontinuity or there's masked pixels, you just don't include it. And you figure most of the sky, most of those contributing epochs aren't going to have something wrong. So maybe you'll throw away 1 epoch on average, or maybe 2 when you've got 100 epochs per object, but that's not a big hit. And the result is that you've got a nice clean PSF with no discontinuities for each of those postage stamps. And once you've got that, you can go do your final deblending and measurement on the postage stamp coad. Now, deblending is in brackets here because you've just made a postage stamp coad, and you can't easily run a deblender on one postage stamp or some other postage stamp that's sourced from the same pixels but has a slightly different realization because it's a slightly different number of epochs. Okay, so then you might think, well, what if I just made a postage stamp coad per blend instead of a postage stamp per object? And the problem with that is some of our blends are enormous. As Fred said, not many of them are, but some of them are big enough to cover a significant fraction of a patch. And now you're back to the same problem. If you threw away any epochs that had a discontinuity or mask, you'd throw away all of your epochs and you'd have nothing left. There might be ideas in between, but overall, this is an idea that I think solves the edge problem at the expense of making deblending harder. And deblending is hard enough. I don't want to add anything to our processing to make it more difficult. A similar thing that you could do, and I think what we're leaning towards right now, is building coadds in very small, say few arcsecond cells, again, postage stamps, but you wouldn't center these on individual objects. Instead, you can build these up front. These can be the only coadds you build. You can build them as direct or likelihood transformed to decorrelated coadds. Just as with the project coadds, you would reject any input images that have discontinuities or masked pixels. You can propagate the PSF by assuming it's constant over a cell. That's actually really nice because you propagate that PSF once and you don't have to go back and do it again and slow things down. And when you coadd a single cell, you would include a PSF with overlap so you can smooth for detection or decorrelation, but only that. Other than that, you'd say assign these cells up front so that they are directly adjacent to each other. And the result is that you get a coadd that has a piecewise constant PSF. That's not something we're totally used to dealing with, but it's pretty easy to imagine how we could write all of our algorithms to work with a piecewise constant PSF. If you're doing detection, you can just detect in individual cells in terms of finding above threshold regions and then stitch those above threshold regions together. If you have an algorithm that's based on forward modeling, as I think most of our algorithms are these days, it's just piecewise model evaluation because you know exactly where that piecewise constant PSF changes. There are some tricky things that I don't know how to do, like aperture photometry, but I also suspect that aperture photometry doesn't care deeply about the PSF being discontinuous. And you can probably ignore this for the algorithms that aren't essentially forward modeling algorithms. I do think there's a complication here that the noise correlations at the borders in particular are going to be hard to propagate, but they're easy to Monte Carlo. And I think some of our more sensitive algorithms, especially on the shear side, really don't need many Monte Carlo samples of the noise in order to get things right, say 1. I've already mentioned Kaiser and decorrelated coaddition. I think this is something we're still actively considering, and the big question is whether the extra complexity in the implementation is worth it. I don't think it is just for the signal or noise. It's possible the seeing distribution will be so broad that it is, but it hasn't. I think if you do the calculation of whether you gain for any existing survey, it's not enough to be worth it. Of course, that's the judgment on how much worth it is to do some software engineering. But I do think it's worth considering because not having to think about which images to reject is really attractive. I mean, if you have to decide which images to keep and which images to throw away when building coadds, you get into all kinds of trade-offs between different science cases. And if you can get one coadd that you know is going to satisfy everyone, that's really nice. Finally, I mentioned that this might be a way around our correlated noise problems. I think if that's true, it looks like it might be with some toy implementations, but we really need to scale this up to running on real data and non-toy scenarios. But if it pans out, that's probably on its own reason to use Kaiser coaddition. Something I haven't talked about, and actually the last thing I will talk about in this talk, is multifit. So those of you who followed the project since certainly the beginning of construction will recognize that multi-epoch fitting has long been described as the way that DM will perform its most systematic limited object measurements. And that includes both stellar motions and galaxy models, especially for shear. This is changing. I think we in DM no longer believe that multifit is necessary for these measurements, and it's a very inefficient way to use scarce compute resources. You just heard Fred talk about how deblending could really benefit from having a bit more in the way of compute resources. And in the original plan, almost all of those compute resources were going to multifit. We're still working on changing the baseline documents that still refer to it. So if you are reading descriptions of what we'll do, they may not necessarily reflect this change. And I will certainly be speaking more on this subject in later talks, specifically my Wednesday talk on astrometry and my Thursday talk on shear estimation. So I realize I have not yet said anything that should convince you that you don't need multifit. This is just a preview, and I'm hoping to be able to convince you, or at least to convince you to have an open mind about it later in the week. And that's it. Thanks.
Okay, thank you, Jim. Big round of applause for Jim on Slack. Do we have any questions lined up? We have some hands raised. Just a second. We'll see what our ordering is. Okay, Paul Price, you are up first. Just a second. Paul, you should be good to go.
Okay. So what's the difference between cell-based coads and just making a splined up version of coad PSF just to sort of cache it, make it go faster?
I think that's the splined up coad PSF only helps you with the computation problem at the expense of potentially killing you with the discontinuity problem. Because it's that a coad PSF of the sort we make right now still has discontinuities that could land anywhere. And so whenever you evaluate it, you have to check whether you're at a discontinuity. And the spline is not going to handle those discontinuities well. The cell-based coad is really piecewise continuous at particular boundaries, because instead of letting the discontinuities land wherever they would by adding all the data we have, we're explicitly rejecting images from the coad only at the granularity of those cells.
Okay.
Thank you.
Massimo, you're next in line. Go ahead, Massimo.
Yeah, thank you. Hi, Jim. The idea of the cells is quite interesting, and if I correctly understand, you just assume that PSF is constant along a single cell, which of course is good depending on the precision you want to achieve with your photometry. I was wondering if, given the map of the PSF that Joshua showed us, which is rapidly varying at the edges of the field, probably you don't want a fixed size for the cells, but smaller and smaller cells as long as you approach the borders of the field, right?
Well, so with dithering, you don't have any space on the sky that is only edges or never edges of an individual focal plane. So I think the way I would respond to that problem, because I think that is a real problem, ideally we can make the small cell small enough that the PSF can be considered constant across them, even at the edges of the focal plane. If that falls through, I think I would be more inclined to say that we should make the PSF, say, piecewise linear, so piecewise, have a linear variation, first order polynomial variation, and then on up, rather than saying constant, before I would change the cell size in response.
Okay, thanks.
Okay, next is Conrad. Just unmuting you.
Hello.
Go ahead,
Hi,
Conrad.
Jim.
Hey.
So you seem to be focusing on producing one single coad, whereas I can imagine that many people would want a coad with the best, let's say, half of the seeing or the best quarter of the seeing distribution. So how broad a seeing distribution are you expecting, and is this something to think about?
I think this is a very interesting question, and I think I have a bit of a contrarian answer to it. I think it's a common assumption that you want to make a coad of the best seeing data, and the result of that is, of course, that it's a lower signal noise coad because you've thrown away a lot of images. But resolving objects depends on signal noise as well as resolution, and I don't know that I've ever seen a convincing argument for making a best seeing only coad from a real rigorous statistical perspective. And maybe that means that I could certainly believe that there are algorithms that you could run on a best seeing coad that would be hard to use on a full depth coad. But a better algorithm might be able to get the same information out of a full depth coad. There's certainly a trade-off.
For example, think of something like looking for very close binaries, for example.
Yes, I certainly agree that there's an inflection point. There's a trade-off at which some point, for some seeing distribution, adding all the images definitely hurts you for direct coads. But if you are using PSF modeling, using your PSF model to separate things, it's, you know, adding another image that's has worse seeing than all the ones you've already added isn't necessarily a losing proposition. So I guess my philosophy is, if that really matters, I would rather invest the time in making Kaiser coadds that really are going to be truly optimal for every scenario, rather than trying to make best seeing and other variants coadds based on different selections of input images. That of course depends on those Kaiser coadds actually panning out and working the way that they ought to. And I don't think that's been shown at scale, but it's been shown well enough, I think, in simulations and with smaller scale implementations that I'm reasonably confident it will work.
Okay.
Okay, next we have Eric Geiser. Go ahead.
Yeah, thanks for this talk, Jim. I'm wondering if you could just directly contrast for us the difference between the postage stamp coadds and the cell-based coadds.
I think the simple answer is the per object coadds are centered on objects. So you have to build some other kind of coadd first in order to figure out where to put them. And then you have to trust whatever deblending you've done on that first coadd, or you have to be much more clever about deblending in order to do deblending on the postage stamps. The cell-based one, I think you can get away with only making that coadd and doing all the processing on that coadd, but you have to rethink how you do your processing on that coadd to be able to deal with the fact that you will have known discontinuities through the middles of objects. And if you can handle having a piecewise constant PSF even on a single object, then I think that's clearly the way to go. And the question is whether there are enough algorithms where you can't do that to torpedo that idea.
Okay, Gary, you're next.
I'm actually asking a similar question to Conrad about, making seeing split coadds maybe as a compromise between your methods. Not so much just to have the one nicest one, but if you do seeing PSF-matched seeing split coadds, then you could potentially the adjustment kernel that you need to apply to each is more compact, and you could potentially carry a 3x3 correlation matrix or something along, and then equalize the noise across those and make your Kaiser coadd from those, right? Kind of a two-step process. I wonder if you've thought about this kind of thing. I know Tony had talked about this a long time ago of making these seeing split coadds. But.
So from my perspective, the big advantage of that is that it lets you do outlier rejection on that first stage. I guess it also gives you a continuous PSF from which to do the Kaiser decorrelation stuff, and that it might simplify the logic there. I think the Kaiser logic is tractable without that. And I think the kinds of mostly temporal, only ever so slightly morphological rejection we're doing right now are working well enough that I'd say we don't need it. But that's a very different statement than saying, if I was starting from nothing, would I go down that path first? I think it's at least an interesting idea, especially from that perspective.
Okay, Paul Schechter, you're next.
Well, I can't give you a rigorous proof that getting the few best images is better for separating close binaries than working on the stack. But I've been looking very hard for gravitational lens quasars in DES, and that certainly is my impression. Now, you said you wanted a rigorous proof, and okay, maybe I could come up with a rigorous proof. But then you said, well, maybe you're just not using the right algorithm. So you're stacking the deck against me. Even if I try to come up with a rigorous proof, you're going to say, oh, but you haven't got the right algorithm. And if you only had the right algorithm, then you could get it in the direct images. So let me just say, with Conrad and with Gary, it's my impression that a stacked subset of good seeing images is going to get you something in resolving very close pairs.
Yeah, and I think I would say that it's long been a plan for LSST to create best seeing coads. And if we don't go Kaiser coads, I think we probably would have to. The flip side of the I want something rigorous is that I think there is something rigorous for the Kaiser coads. If you make those, then I think you can prove that no one can do better than that for under those criteria that I think are broadly met. But I think you're right. Well, if you flip the burden of proof around, I think you're absolutely right that I cannot say that one coad will be good enough for everyone for any seeing distribution. And I think there are a lot of seeing distributions for which one coad would not be good enough for everyone unless it's a Kaiser coad.
Thank you.
Okay, Josh, I think you have a question next.
Sure, yeah. So this is basically the same question I previewed about meta detection. What happens if there's a red and a blue galaxy in the same cell?
Yeah. So I think in any form of having chromatic PSFs, you have to coadd the chromatic PSF. And I think that all just flows through fairly straightforwardly. You can still, it means your PSFs are more heavyweight and you have to use 3 numbers to evaluate them rather than 1. And in a cell, you would still have to evaluate the coad PSF in that cell as a function of SED. If you did this with Kaiser coads, it means you can't be optimal for all SEDs at once, but I think that's a very much a second order kind of effect.
Okay, and then the measurement algorithms have to be able to deal galaxy by galaxy still with the right PSF.
Yeah.
Okay.
Yeah, I mean, it punched the problem through coaddition, but it's the same problem you would deal with on single epoch images.
Thanks.
Okay, I'm not seeing any more questions. We have well, we're actually exactly at 2:30. Does anyone, we could take a couple more questions, I think, if people want to ask any. Tony, do you have a question? I've just been prompted that perhaps Tony Tyson had a question. Tony, I unmuted you now if you were saying anything. Okay, so I don't have any more questions. Thank you again, Jim, for that that excellent talk. And I want to thank again, I want to thank all the speakers for today for their talks, for the work and efforts that's gone into them. Just bring up the agenda. Okay, so yeah, it was a great day. I don't have the recordings yet. I know some of you had to drop out to go out and teach, to do other things and so forth. Some people have asked me about getting the recordings. I don't have them yet. And I'm told that Zoom is a lot slower than it usually is. So I'm not sure when I'm going to get them. I'll make them available in the participants drive probably when I get them. So for tomorrow, we start again at the same time, 9 a.m. project time Pacific. The Zoom room will be open 15 minutes in advance for people to connect, but I don't think we had any real connection problems today, so I'm not concerned about that. And as for today, we'll try and make the talks available in advance in the participants drive so people can download them and have a look at them in advance. So other than that, thank you very much again, everyone, and see you tomorrow.